If you look at all of this and you take these equations seriously, right? The total energy is, given here. Rest energy, E equals mc squared, and that's really the part this is about, right? This, and probably you want to look at this more like m equals E over c squared. This is really what Einstein derived this, and I think I linked the paper in the course plan if you want to read it. That's really what this is about. Like, it's saying, well, what is mass, right? What is this quantity that you're measuring? E equals c squared, or E divided by c squared is sort of what mass is or whatnot, right? So energy is the real key part there, and it's a really change of perspective of what mass is. And yeah, it's not just frozen energy. This a common one here, that mass is a form of energy. No, Einstein definitely wouldn't say, if you really take that seriously, that's not really what it says. Or, and this is a big one, and I kind of use it a little bit myself sometimes, but it's strictly speaking not really what this is saying, right? That mass can be converted into energy or back and forth. A really common one, and sometimes it's just kind of useful to say, but technically, no, not really what this says. And here's an example that might sort of draw some or shed some light on that. We have two identical clocks are placed on scales, and let's assume these are very, very, very precise, infinitely precise, if you will, hypothetical scales. Now, one of the clocks is working and the other is not, right? Which one has more mass? So I just to give you a visual, right? We've got a situation like this, two completely identical clocks. This would have more mass, right? Yeah, not working. And this is really because of that, right? That it's saying, well, what is this thing that you're measuring when you're measuring the mass of an object? What is this thing? And that's where it comes into here, right? Recall, right? Mass is E over c squared. So if one has more energy, right, because it's working, then it should have more mass if you could measure this precisely enough. And that really gives you, if you want to really, like I said, take this seriously, then what you're really saying here is that mass is a property of energy. Right? It's just something that we can measure, that, okay, you've got mass, or you've got energy rather. If we can put this on some sort of scale or measure it, that's essentially what we're getting a reading of, right? That the mass itself is this sort of fictitious thing that we've made up. And we've kind of encountered different things like that in the course that have been fictitious. But in that sense, it really is. It's saying, well, like, this idea that mass was the amount of stuff, right, was a little bit of misleading, right? And in grade 11, usually for your first physics course, that seems like an important step you're learning, right? We're saying, well, actually, weight is the force on some mass, but mass is technically the amount of stuff. But now we kind of come to the next level of this and say, well, actually, mass isn't even really a thing, the amount of stuff. It's just some property that you measure because things have energy, right? If you really look at it, even you want to look at more of an atomic level or subatomic level, what is going on here, what is actually happening that would give you some reading of mass is, really potential energy within, like, all of those atoms, if you will, right? Or quarks, and we'll get to some of the fundamental particles there, but that's really what this is saying, that as you understand it, it's not really a thing. Now I'm probably going to use it as a conversion because that's typically with calculations or whatever we do. But remember, at the end of the day, any of these things really can be looked at as conservation of energy. So anytime you're looking at one of these things or questions or problems that has this sort of conversion, just remember, really, if you were being really strict about what that equation means, it's just conservation of energy. It's just changing energy from one form to the other. It's some potential energy within some, electron or whatever, and then it is converted to a photon and goes off, right? That's really all that's happening, is energy changing from one form to another, not mass. So anyway, the average home in Canada uses 3.6 times 10 to the 10 joules of energy per day. That's a healthy amount. Probably not sustainably globally. How long could a cabbage with a rest mass of 0.75 kilograms supply energy for the average home if all of its rest energy could be converted to electrical energy? So again, we're already sort of using that, but again, if you imagine all the potential energy within all the subatomic and even particles is a bit of a stretch, but we'll say that if that was all converted, or all that energy was converted to photons of light with energy that could somehow be used as electrical energy, how would that work? Well, the calculation, again, the rest energy, this is just mc squared, right? We're given the mass, and so we get an amount of joules. And you can see, because you're multiplying by c squared, that's a lot, right? That's a lot of energy. And so then to get the number of days, okay, you just take that amount of energy and divide it by the amount of joules the average home uses per day. And that gives you 1.9 times 10 to the 6 days. Since you use about 300, or there's 365 days in a year, or 0.25 if you prefer, that's about 5,000 years, right? One cabbage, one home for 5,000 years. Not bad. I already started working on this one a little bit, just to sort of get through and help us, speed along, but please stop me if you want to. Proton moves with a speed of 0.8 c through a particle accelerator. In the accelerator's frame of reference, right, not the electrons, calculate the total and kinetic energies of the photon in mega electron volts. So I put a little note here just because you'll see this term a lot, particularly with particle physics. So a mega electron volt, well, first you want to look at what an electron volt is, and that's what I denote right here. So an electron volt is just the energy gained by an electron when it's accelerated by a potential difference of 1 volt, right? So that's 1.602 times 10 to the negative 19 joules. So just take that, like this is just another type of unit. You could use joules, you can use electron volts, right? And since this asks for mega electron volts, well, 1 mega electron volt is just 10 to the 6, or 1,000,000 electron volts. So just multiply this number here by 10 to the 6, which really just changes the 19 to negative 19 to negative 13. And so all I did was use the equation I had on the last page. If I want the total energy, that's just, again, mc squared divided by 1 minus v over c squared. Plug in the numbers. Hopefully this looks okay. That's all I'm doing, is taking the mass of an it is a proton. So last time when I did the question earlier, I had a electron. I thought I had that again, but yeah, so the mass of a proton is 1.6 times 10 to the negative 27 kilograms. So I'm just keeping everything in SI units while I'm doing this. C squared is right in there, and then you can see the denominator. That works out to this number here. Again, that's in joules, the 2.505. So you could just take that number and divide it by 1.602 times 10 to the negative 13, and that's fine. But sometimes I find writing it this way, if you write it as a multiplication and you put the units in, sometimes that's a nice way to make sure units cancel, right? Because technically, if you look at the first number, right, this is all over 1, if you will, right? It's a numerator. And And so if I want to make the joules cancel and I want to be left with just MeV, so I take the relationship that I know, 1 MeV, right, equals 1.602 times 10 to the negative 13 joules. So if I take that and just put that into a fraction, right, and then again, the 1 MeV I put on top because I want MeV on the top of my calculation. And I want to cancel out the joules, so I make sure I put joules in the denominator. And so then what happens is the joules cancel, and that leaves me, in terms of units, it leaves me with just MeV. But because the 1.602 is in a denominator, I divide by it. That leaves me with 1.56 times 10 to the 3 MeV. Good amount. Part B, I want the kinetic energy of this proton. And then I just use the fact that kinetic energy is total energy minus rest energy. I just calculated the total energy, and so I'll go back and just use SI units. So I'm just using this number up here, and I'm just going to minus the rest energy. I haven't calculated it yet, so that's just mc squared. That's all this term is here for rest energy. The mass of proton times c squared. Do that subtraction. I just did it in a calculator, and I get 1.002 times 10 to the negative 10 joules, or 0.625 giga electron volts. And a giga is just 10 to the 9 electron volts. So just to mix it up a little bit.